Hi, everyone. Sorry for the transition here. We just had to get laptops and everything switched over. But for those of you who were here before, it's me again. I'm Jeremy Stratton-Smith, and I will just sort of be introducing and guiding our talk today as we go through the new developments in step-by-step mathematics. We have a whole range of content that has come out in the past few years, and we're really excited to be able to share it with you. So sort of as an overview of the Wolfram Alpha step-by-step functionalities, we really have broken our approaches into two different procedures. Whoops. Okay. I think we're good. So the first and sort of easiest to write step-by-step code is for procedural processes. So this is anything like taking a dot product, figuring out linear independence, computing an arc length, something where there's essentially one or more procedures that are rote, and you do those and you get an answer. The second method is rule-based, which is essentially making use of the Wolfram language's great ability to do transformation rules and applying a set of transformation rules to an expression until we reach some sort of fixed point. So this is great for things like doing expansions, doing simplifications, doing algebraic manipulations, and so on. Through both of these approaches to our step-by-step code, we have a sort of unified structure, which is that a single step in a step-by-step program is broken up into a hint, which is sort of guiding the user along, a textual description, which is sort of stating what is happening in this particular step, and then some sort of printed out transformed expression. So because we have a lot of content to go over today, I'm going to, I guess I'll show one of these just so you get the idea, but you're going to be seeing lots of steps today. So I'm not going to spend a long time working with these examples right now. Oh, there it goes. Okay. So you can see here, this is our introduction. And as we go on through the steps here, we get a hint. Oh, I'm sorry, I hit evaluate twice. We get our hint, which in this case is just sort of giving you the beginning process and describing what linear independence looks like. And as we go along, we get our textual description and the printed out math expression here. So with that, I believe I'm going to be handing it over to Anne-Marie, who's been working on our long arithmetic.
Good morning. My name is Anne-Marie, also a member of the Wolfram Alpha math content team. And one of the projects we've been putting a lot of time into over the past year is expanding our steps for long arithmetic. So when we start thinking about what long arithmetic is, one place we can start are the Common Core standards for math. Up on the screen, I have selected a few of the Common Core standards related to long arithmetic throughout several grades. And if it looks like a lot of words, that's how a lot of teachers feel too. So we're trying to sort of distill some of the main points that students and teachers are going to need to use in the classroom and make sure that those are woven into the steps that we're providing online. So by reading closely all of the standards, there are three things that recur throughout the grade levels. And long arithmetic involves strategies based on place value, base 10, having a written method to express that strategy for arithmetic, and then using a standard algorithm for each of the arithmetic operations. So many of us will be familiar with some variation of a standard way of doing arithmetic on paper. We have notions of, in Common Core words, composing and decomposing. I learned it as carrying and borrowing, and sort of referencing all of that with this conceptual understanding of place value and how digits are arranged. So that's part of what we've tried to implement in the steps. And also, of course, there's a written method, which is kind of a trademark of this long arithmetic, is that we have for each operation a specific type of grid or arrangement of the digits that we use to keep track of the procedure as we write it down. So those are what we've built for our steps in long arithmetic. Now, for this audience, I don't think I'm going to go through in detail all of the arithmetic steps one by one, but I want to show some of the expansions to the scope and that we've supported. So we already have had for a long time. It's a great place to start if you're doing step-by-step programs, arithmetic with whole numbers. So you can ask for the step-by-step solution to here's a subtraction of two integers, and you will get all of the steps in that hint textual description printout of the, in this case, the written grid for the long arithmetic procedure, long subtraction. So we've got the written method described. How do we align the digits? Thinking about probably a potentially younger student or a teacher of younger students that has to not lead too many details. And working through one at a time to explain the borrowing using the place value language, and so on and so forth until we arrive at an answer. And there we have a long arithmetic of whole numbers. All right, well, we also have negative numbers introduced at some point in that sequence around 4th grade in the Common Core sequence or whatever set of standards your elementary school is using. So we've also added a little bit of extra support just to make sure that we can provide steps for arithmetic with negative numbers in different operations. For subtraction, we have sort of just an intro step to address that we can express subtraction of a negative from a negative as addition, and then interpret that as a negative number. We do something similar for multiplication, where in this case, negative times a negative is a positive, something that my students can just like recite. That's something they know. Negative times a negative is a positive. And so we've just implemented that, which expands all the different steps we can provide without adding too much more of the code. It's just this extra explanation to allow negatives. Another expansion that we've done, a little bit more involved, is to do step-by-step for decimal long arithmetic. Here we have to make sure that we're being careful about that place value reasoning so that we have decimal points lining up in the case of addition, making sure we're padding all of the extra place value places, and then referring to the different place values as we go through the written method. For multiplication, for example, if we're doing multiplication with decimal numbers, the extra content that we added comes at the end in this sort of procedural trick of counting up the digits after the decimal in each of the factors, and then having that be the number of digits after the decimal in the product. And then one other consideration that we've taken into account is that for division in particular, there are different, well, for all of the operations, there are different contexts in which they're used. For division, you can report your answer in a few ways. So we have some different methods. You can see the step-by-step long division algorithm with the division grid. So we have our written method. And then we can make a conclusion that we come to a quotient with a remainder, or a teacher might ask for that answer to be reported as a mixed fraction instead. And so we've built out just a little bit around those division steps this is the same steps, but now with an extra step at the end of how to format your answer in the desired form. Okay. And then another thing that we're working on, also in the Common Core standards, you can do arithmetic with polynomials. So we've also been building out our long arithmetic steps for division with polynomials and multiplication with polynomials. So I won't go through all those. We've got the ones for steps to go to, but those are available online. And we also have a lot more to work with. So I showed you multiplication and subtraction, and we have addition with decimals. We're working on adding the support for division with decimals. We also are thinking about showing long arithmetic for bases other than base 10. And then something that I really enjoy working on are alternative methods for long arithmetic, or various types of mathematical procedures, things that may have visualizations or different arrangements of that written method. There's some room for interpretation when it comes to the standard algorithm geographically based on different teachers. So working to expand our content to match those things too. Okay, so now I will pass off to Jordan, who's talking about trigonometric simplifications.
Thank you, Anne-Marie. So today we're going to be talking about trigonometric simplifications. So with regards to Wolfram alpha, we had to first be able to evaluate various expressions and simplify arithmetic and integers and rational arithmetic, combine like terms, and be able to multiply expressions using the binomial theorem and distributive properties before we could get into simplifying trigonometric expressions. So what I'm going to do today is going to be talking about what are called identities. So you may have seen an identity such as sine squared plus cosine squared of x equals 1. And we've had this functionality since 2012. So what we're adding this new now is what are going to be simplifications. So we're going to either have an expansion or we're going to have a reduction. And so we have different types of simplifications that we're talking about. So for instance, what's called a power reduction is this last formula above, this cosine squared of x minus sine squared of x. Essentially the reverse of that would be when you take the double angle formula for cosine and make that into cosine of 2x. And so we have both of these simplifications that have been in production. So right now, the functionality is working with sines and cosines, and this will be expanded in the future. And then we're also going to be able to support specific types of expansions. So if you're expanding out your cosine of 2x, sometimes that's written in terms of only sines, and sometimes that's written in terms of only cosines. And then there's also, in the future, we're going to have factoring. But one idea that you can think about here, if you're trying to understand this from a conceptual programming viewpoint here, is that you can think of these trigonometric simplifications as sequential applications of rules. So as Jeremy was mentioning at the beginning of the hour, there are rule-based methods, and simplifications are one example of a rule-based method. So you could take a look at an expression such as sine of 2x plus cosine of 2x, and you want to apply various rules here to be able to expand that out in terms of powers. So we have the sine of 2x. We recall that we have this double angle formula for sine, and so we can apply that. And then we can also, after that, apply a double angle rule for cosine. And so that we'll see that if we expand this out, we would get 2 sine of x cosine of x plus cosine of x squared minus sine of x quantity squared. And so what is going to be the tough part here? Well, the tough part is that there's a wide variety of different rules that could be applied at any given step. And you want this to be in a readable format that a student can understand. So for instance, there are some rules that take on a paramount importance in your trigonometry class, such as a Pythagorean identity. There's the equivalent sine squared x plus cosine squared x equals 1. And then you can derive further identities from that. But what happens is you can think about this from the viewpoint of there being looking at the entire expression and working inwards, and then also a viewpoint of building up and thinking about this. One way of thinking about this would be as an expression tree. So for instance, when you're applying rules here, you could start, for instance, from these leaf nodes here. And then as you're looking up this tree, you'll encounter a cosine, and that will have cosine of 2x, and you'll want to apply a rule there. Then we could be next step applying a sine rule. And then after that, we could be computing out a power of that cosine. So that's a little bit of the idea behind this rule-based simplification of trigonometry. Sometimes scanning the entire expression can be computationally expensive. That isn't always going to be the case. So for instance, you could save a lot of effort in your steps if you were looking at something such as a sine of 2x quantity squared plus cosine of quantity 2x squared. and recognizing that as one instead of expanding things out and then simplifying that further there. So right now we have, so I put polynomial in quotes because right now we're supporting polynomial functions. So we haven't gotten to rational functions for these simplifications yet, but that is in the planning stages and pre-planning stages. And then after this, we plan to be further expanding to exponentials and logarithms, and then converting between exponentials and logarithms, and converting between trigonometric expressions and exponentials. So now I'm just going to go over an example of this here. So in Wolfram Alpha Notebook Edition, you can type in step-by-step simplify of sine of 2x plus cosine of 2x. We can simplify this out. We see that we can apply the double angle identity. And again, the double angle identity is sine of 2x equals 2 times cosine of x times sine of x. We can apply that. Then we can apply a cosine double angle identity formula, which is again cosine of x quantity squared minus sine of x quantity squared. And then we can combine all that. So for an example here, these can become more complicated, such as the following. So we now have cosine of x squared minus sine of x squared plus 2 sine of x cosine of x plus cosine of x squared plus sine of x squared. And we want to reduce the following. So think of taking what we had done before and reversing that. So now we're trying to simplify this into a formula with a multiple argument here. So we have the double angle formula can be applied here. In particular, we could start by looking at the double angle formula for cosine, which is our cosine of x quantity squared minus sine of x quantity squared equals cosine of 2x. We can apply this. Then we can denote the Pythagorean identity here. And then we can also apply the double angle formula for sine. And after simplification here, we return this formula cosine of 2x plus sine of 2x plus 1. I want to point out that there's been a lot of effort towards the Common Core standards here. So in the Wolfram Alpha Notebook Edition, as Anne-Marie was demonstrating, we have the ability to work with Common Core standards, and we can obtain information on the trigonometry standards, for instance. So in particular, there are two trigonometric function, and then we can also get that definition as well. So we can get information on the Pythagorean identity of sine of theta squared plus cosine of theta squared equals 1. And then, as mentioned, we can earlier, we can use that to find various other Pythagorean identities. And then we also have another standard here for the Common Core. So now I'm going to play a short video here developed by our intern, Judy Zhang, for statistics.
Hi everyone, this is Judy. I am an intern at Wolfram for the summer of 2022. The goal of my internship is to develop step-by-step solutions in the statistics domain. So here is an example of the step-by-step solution for performing a two-sample Wilcz's t-test. So when a user inputs a query for conducting a two-sample Wilcz's t-test and clicks the step-by-step solution button, she will see a detailed step-by-step instruction on how to perform a two-sample Wilcz's t-test using the data she has entered. So this step-by-step solution first introduces the problem, including the testing hypothesis. The user input data are shown here in this table. Following the instruction, there is a list of steps required to perform this two-sample t-test. The next few steps contain instructions on how to calculate the t-score, the degrees of freedom, the tail probabilities, and the p-value of the test. For each of these steps, there is a hint that discusses the significance of the step, and an explanation on how a value is derived by using appropriate formula and performing the calculation. The user can see the detail of these calculations by clicking the value inside the yellow box. For example, this shows the step-by-step detail for performing the calculation of the integral. The last step in the solution is to give a conclusion about the test based on the calculations done above. A decision on whether the null hypothesis is rejected is given based on the input data. The user also has control over the directionality of the t-test. The user can choose the direction of the t-test from a drop-down menu containing options to perform a two-tailed t-test, a left-tailed t-test, or a right-tailed t-test. And here is an example of a right-tailed t-test. The structure of the test is very much like the two-tailed test. Besides these two sample t-test projects, I have also worked on developing a step-by-step solution for the f-test of equivariances, which is another popular hypothesis test with similar steps, but is used in a different scenario.
I'm going to play a video by our developer, Carlo Andres, who is going to be talking about vector calculus in regards to the gradient function.
Hello everyone, I'm Carlos Ballesteros and I'm joined Wolfram Alpha my content team 6 months ago. And since then, I have been working on the step-by-step solution for vector analysis part. Today, I'm happy to show the new feature of this topic. So let's go. For vector analysis, now there is a step-by-step solution for gradient in Cartesian coordinates. But what is the gradient? I will try to explain this in a easy way. The gradient is a vector constructed from the partial derivative of a scalar function. For example, if we have a function of 3 variables, then we will get a 3-dimensional vector with this form. Let me use this example to show how the gradient works. And if we have this function here, then we can calculate the gradient and plot the vectors along the domain, and we will get this. Something useful using Mathematica is that we can project those arrows along the surface, and then we will get this function. Something interesting about gradient is that the gradient is the maximum value at direction of the directional derivative. That means that if you need to move along this surface, you should use the gradient. I mean, you should use one of these paths because they are optimal paths. Something interesting, I mean, I have one curiosity about curves and hill. When I was at the university, my teachers say that when the curves spend a lot of time going up and down the hill, at the end they use one optimal path. That means that the curves use the gradient. I don't know if this is true, but if you know something about it, please let me know. Great, now let's see how the step-by-step gradient works. For it, let me go to the website. And then, yeah, great. For this query, this is the function from the example. We can see the step-by-step solution. And essentially, the first step is the introduction, but the second step, I think, is the main step for this solution, because here we give the definition for gradient, and then you only need to calculate partial derivatives to construct the vector solution. As you can see here, we can use, we can see the intermediate step using this button, and we can see how calculate the partial derivative. This function works for queries like this. Let me change the function. We have one more coordinate. Great. You can see here. One second, yeah. We can see the step-by-step solution. Again, we have the step-by-step. We have the definition for gradient in 3 Cartesian coordinates. And then we only need to calculate the partial derivative. First with x, then with y, and z. Yeah, that's all from this function. And in the future, the idea is have the step-by-step solution for divergence and for curl, and add alternative coordinate systems. So yeah, that's all from vector analysis part. I would like to show in the next Wolfram test conference more step-by-step solution for this topic, for this subject. So thank you for hearing me, and that's all. Bye-bye.
So now Jack Heinraf will be talking about discrete mathematics and number theory.
Thank you, Jordan. Yes, so we have also continued working on step-by-step solutions to discrete mathematics problems. This year, particularly in 2 areas, we introduced a lot of new step-by-step functions. The first area is solutions to recurrence relations. And so recurrence relations are the discrete analog of differential equations, and we have had step-by-step solutions for these kinds of problems for many years, I believe since at least 2015. And a first course in discrete mathematics will typically cover 3 to 4 techniques for solving linear, finite order, constant coefficient recurrences. We have so far implemented 2, which I will talk about below. And these methods are typically, or these recurrence relations are typically subdivided into 2 classes: homogeneous ones, where they can be written in the form of an equation equal to 0, and non-homogeneous equations, where our recurrence relation is equal to some function independent of our unknown function f, where p is typically a constant, polynomial, or exponential function. And the currently implemented methods that we have are the characteristic polynomial and generating function solutions for homogeneous recurrences, and the generating function solution for non-homogeneous recurrences. Additional techniques that we're thinking of are, for now, probably just the eigenvalue method. There are more advanced techniques, but they aren't typically in the scope of a first course in discrete math. I say here that specifying boundary conditions for these problems will also be an option soon, but actually it's already working. Okay, so some examples. Probably the most famous recurrence relation, and the first one that students are introduced to, is the Fibonacci equation. And we can now show how to find a solution to the Fibonacci equation using, let's say, the characteristic polynomial method, which is, I mean, I don't want to go into the details of this method. It basically uses techniques from operator theory, but a student doesn't need to know that. They're just given a formula for a polynomial, which they can construct given the recurrence relation. And then it's enough to find the zeros of this polynomial. to JIT. Here are the zeros with their multiplicity. And then there's a sort of inversion formula where from the zeros of this polynomial, we can construct the fundamental solutions of our recurrence relation. And then combining those in a linear fashion, we get the general solution to our recurrence relation, which in this case is this, but also Wolfram alpha is clever enough to know that this can be further simplified to the sum of the Fibonacci equation, Fibonacci numbers and the Lucas numbers. This would be further reduced if we introduce boundary conditions. So let's look at an example with boundary conditions involved. And this is also an example of a non-homogeneous recurrence relation. The number of steps required to solve the Tower of Hanoi problem. I think everybody here should be familiar with the Tower of Hanoi problem. It's basically a simple game. And yes, here we have this solution where this technique is a little bit more involved because it requires us to use generating functions, formal generating functions. The student would need to be able to manipulate those correctly, and then also use a little bit of Taylor expansion, or at least differentiation, to find a Taylor expansion for the closed form of the generating function. And this finally gives us, after substituting our boundary value, this gives us a solution to the Tower of Hanoi problem. Another area that we've been working on is elementary number theory. Here, the steps that we implemented are somewhat simpler. We just implemented step-by-step solutions, step-by-step evaluations, I'm sorry, to various number theoretic functions, which are typically introduced in a first course in analytic number theory or general number theory. I don't think these are evaluated, so I'll just evaluate them here. And these all follow a very similar structure. So to compute the Mobius function mu for a given input, we first remind the student the definition of the Mobius mu function, which all of these functions are basically functions which tell us something about the prime numbered factorization of our number. And then, so we remind the student of the definition of our function, we find the prime factorization of our number, and then we just apply the definition to the prime factorization to find our solution. And the same goes for the Louisville lambda function. I will just quickly evaluate these and show these, but I won't go through them in details. Again, we have the definition, the prime factorization, apply the definition, and it's the same for the remaining three. Yeah, here you can see we have, again, definition, factorization, solution, definition, factorization, solution, and finally definition, factorization, and solution. And we're thinking of adding more. We already had some. We had the Euler-Toshin function and the sigma summatory functions implemented. We're thinking of expanding this to cover more and more of an analytic number theory curriculum. That's it from me. Thank you very much. And I believe I hand it over back to Jeremy.
Awesome. Thanks, Jack. So as you can see, we have a lot of projects going on, and this is not only the only domain in which we have step-by-step content being developed. We have physics and chemistry steps that are also being worked on presently, and in an ongoing way. So it's an exciting thing to have so many folks on our team who can really be developing and putting out such a breadth of step-by-step content. So at this point, I think it would be great we can take any questions if you'd like. I will also point you all to the Wolfram Alpha website, where you can see more examples and really sort of dive into the existing areas of step-by-step content that we have. This has really been one of the prime features of Wolfram Alpha, and as you can see, there's always more work to do as it goes in math, and we're excited to be able to continue. So if there are particular things that you want to see that we do not yet have, it's always great to get recommendations and requests from folks as well, so that we can prioritize that and get them in. So yeah, thank you all so much for coming. And if there are questions, we can take those now. Yes, and I think that's a good question. So yeah, the question of providing the justification for why you're doing things, is that sort of what you're getting at? So I think, and I would encourage anybody else on the team to also jump in if you'd like. I think the general approaches that we've been taking is that the hints, and I would encourage you, and we can look through some more examples if you'd like, but the hints are oftentimes really trying to get at that why, and prompting students with a, is this a situation where you might apply this particular thing that you know about, or is it getting, and I don't know, there's so many different areas, it's hard to generalize a little bit, but I think that and maybe what you're talking about would be addressed by, having at the very outset of a problem, this is the strategy that we're doing, which is the approach that the chemistry developers have taken, that at the beginning of the problem, instead of really having hints throughout, they say, this is how we're going to approach this overarching problem. Yeah, and I think the part of the reason we haven't done that for math is, as you're going through a problem, maybe there is a general principle at the beginning, but oftentimes as you go through the process of solving a math problem, the general principles that you're using might change, right? So if we just have a list of things at the beginning, it's not paired with where is that actually being applied and how does that fit into the overarching process. Yeah. Does that address things? Right. Yeah. Right. And I would also put in there that when I would also put out there that as we have been fleshing out the breadth of content that we have covered in step-by-step functionalities, we're really also putting in the effort to, where applicable and where it fits, be able to do those intermediate steps as well, right? So for somebody who's doing a calculus problem, maybe some students who are doing calculus don't need to remember how to do a polynomial expansion, but some students might. So if that fits into the problem, we will put details around that so that if the student wants to see that, they can open the details and see, oh, okay, right, this is how I do this polynomial expansion, and then be able to continue on with the rest of the calculus problem, right? So that we're trying to be able to provide content that meets students where they're at in terms of the difficulty of the problem at hand. That's a good question. So the question is, I don't know if everyone could hear it. Essentially, how do we determine the number of steps that we're going to be showing? Are the steps that we're showing considered optimal by some metric? And I would say for the procedural sets of steps, like things like computing an arc length, or I don't know, to a certain extent, some of like the arithmetic that Anne-Marie was showing, those essentially we know how many steps. Well, I guess the arithmetic we don't entirely know, but like, there's a set procedure and you're going to go through until you're done, right? And then we know that we're done. Yeah. On the flip side of things, when we get to looking at the rule-based when we look at the rule-based steps programs, it does become a little bit more tricky to know, because at that point, essentially, you can either do just the procedure of sort of finding a fixed point by applying rules over and over and over again. But in order to really optimize it, we'd sort of be getting into Stephen multi-computation world of seeing where exactly in this large expression can we apply rules, which rules apply the best, and you end up with this big multi-graph thing, and we have not implemented, doing that. And I would also point out, particularly for the trigonometric simplifications and expansions that Jordan was talking about, it's not always, we have to delineate what is an expansion versus a reduction in trigonometry, right? And that's something that students deal with. And oftentimes, I remember being in high school and college and doing trigonometric expansions or simplifications and finding myself going in a loop, right? Because if you apply the wrong rule, you end up doing something that you undo again, right? And we can take steps to try and avoid that happening, but yeah, for the most part, we do try to avoid that. if there are no other questions, I would encourage you to, come talk to us if you want to talk to us about it more. Otherwise, there are there are some past talks as well, but there's also an office hour that all of the math team are going to be at, where the office hour is for Wolfram Alpha Notebook Edition specifically, but we're happy to talk about any of the things that we've been talking about this week. So thank you all again so much for coming, and hope you enjoy the rest of the conference.